Welcome to Chapter 3.1. Today we will be covering systems of two equations in two unknowns. So the first example asks us to determine all solutions to the linear equation 3x minus 2y is equal to 12. Now when we hear a linear equation, we should think of y equals mx plus b. That would be a linear equation in slope-intercept form. Alright, our current equation doesn't quite look like that, so what we're going to do is go ahead and solve this system, solve for y. Alright, so when we went to solve for y, that means move everything else to one side of the equation. So let's go ahead and subtract 3x. We get 2y, negative 2y on the left-hand side is equal to negative 3x plus 12 on the right-hand side. We'll divide through by negative 2 and we get y is equal to positive 3 halves, or 1.5 x minus 6. Alright, so now we have the equation of a line. Well, we were asked to determine all of the solutions to a linear equation. And a line has an infinite number of solutions. A single line has infinite solutions. Alright, so how would we write that out, maybe in more mathematical terms, instead of just saying, well, it has infinite solutions? Well, what we would say is, typically we write out a solution to our general form of a line as an x-coordinate and a y-coordinate. Okay, so here we found that y is equal to 3 halves x minus 6. So our general solution, well, we could say x is x and y is 3 halves x minus 6. This would be our general solution, specifically parameterized by x. That means we still have x's involved in our solution. Alright, so it's parameterized by x. Now, if we wanted to, we could parameterize the same solution by y. If we wanted to parameterize it by y, we'd have to do a little bit more work. Alright, instead of solving for y like we did originally, we would have to solve for x instead. Alright, so let's take our 3x minus 2y is equal to 12, and now let's solve for x. So that gives us 3x is equal to 2y plus 12. Divide through by 3 and we get x is equal to 2/3 y plus 4. So if we wanted to parameterize by y, instead we would say that our general solution, so this is parameterized by x, our general solution, x is now 2/3 y plus 4, and y is y. This one is parameterized by y. Now, if we wanted to go one step further, so again, this was our general solution, we could find a particular solution. If we wanted to find a particular solution, all we need to do is choose one x value or one y value and go from there. Alright, so because it has infinite solutions, any x value will work. Okay, but we have to pick the correct y value, or we have to find the correct y value that goes with whatever value of x we choose. So let's pick something simple. How about we choose x is equal to 0? Well, if x is equal to 0, we need to find the proper y value that goes with that. All right, so let's go ahead and take either one of our general solutions. You can find this using either y is equal to 3/2 x minus 6 or x is equal to 2/3 y plus 4. I'm going to go ahead and choose the first one just because it's going to work out a bit more quickly, and you'll see how. We'll say y is equal to 3/2, but x is 0 minus 6. Anything times 0 is 0. That gives us y is equal to -6. So our particular solution would be x is 0 and y is -6. Alright, so let's continue by now looking at how to solve a system of equations. So the first system that we're given here is x plus y is equal to 3 and x minus y is equal to 1. And we are asked to solve this system in two ways. First, by looking at the system graphically, and second, by looking at the system algebraically. Alright, so first, looking at it graphically, let's go ahead and rewrite these equations in the form of y equals mx plus b. Alright, so let's start by rewriting the equations. So the first one, if we solve for y, we get y is equal to -x plus 3. And the second equation, we get y is equal to x minus 1. Alright, again, here we have two lines. So what can we notice about these two lines? Well, the first one, our slope is -1. And in the second equation, the slope might look like it's not there, but technically there's a +1 there. Anything times 1 is itself. Alright, so our slope, m, is equal to -1, and here m is equal to +1. So when we have two equations with different slopes, two lines with different slopes, ultimately they are going to intersect at one point. Alright, so here they will intersect at one point. Well, we were asked to solve this graphically, so let's go ahead and take a look at a graph to find where they're going to intersect. I'm going to exit out of here and take us over to Desmos. Alright. So let's look at our first equation. Here's y is equal to -x plus 3. This is the one with the negative slope, right? We see it decreasing as we look at the graph from left to right. Now we look at our second line, y is equal to x minus 1. This is our positive slope, so it should be increasing as we read from the left to the right. And we see here that we have a point of intersection. It looks like 2 for our x-axis and up 1 for our y-axis. And here is our point 2, 1. Alright, so that would be how we solve our system graphically. We find a graphing tool and we find the point of intersection. Alright, so our point of intersection is our solution. And our solution is when x is equal to 2, y is equal to 1. Alright, and notice we only have one solution here. In our last example, a singular line had infinite solutions, but in this case, we're looking at two lines. So far, we've only seen the outcome of one solution. Let's look at the same system of equations, but now let's solve it algebraically. So when we say algebraically, it means we have to do the math steps in order to get to the solution instead of looking at a graph. And particularly, we are asked to solve by using elimination. Alright, so when we want to use elimination, we want to combine the equations somehow to get rid of one variable. Get rid of one variable. Because if we take a look at our system, the difficulty is there's two variables. If we can get rid of one of them, then we can solve for one, and it doesn't have to be in terms of another one. It doesn't have to be parameterized by another one of the variables. You see what I'm saying? So if we want to solve algebraically, we are going to take our two equations, x plus y is equal to 3 and x minus y is equal to 1, and we want to do some kind of addition or subtraction to these two equations in order for one of the variables to cancel out. Now you can choose either canceling x or canceling y. Often one will be a little simpler than the other. So in this case, I notice that we have a positive y and a negative y. Those are already opposites of each other. So if we added them together, they would cancel themselves out. So that's the route I'm going to choose. If you would like to eliminate x, you are welcome to do that. Alright, but I want to eliminate y, so I'm going to add this entire equation, and I'm going to put parentheses on this entire equation just so we know that this plus sign gets distributed to all of these components. What do I mean by that? Alright, well, we have x plus x. That's the first thing we're looking at. That gives us 2x. Then we have a positive y plus a negative y. Alright, plus a negative means we are subtracting 1y from 1y. That ends up with 0. And we have to look at the other side of the equal sign as well. 3 plus 1 gives us 4. Now you don't have to write this plus 0 here, but it's nice to have just for completeness. Alright, but that gives us 2x is equal to 4, and one more step, x is equal to 2. So here we have now solved for x. We still don't have our solution because we need to know the solution point. We need to know both the x and y coordinates. Alright, so we have found x, but we still need to find y. And you can do this one of two ways. You can either plug in x to the first equation or plug in x to the second equation. Either one will give you the same y value, since that is where the two lines intersect. They will share the same y value. So let's start. Let's just choose the top equation. X plus y is equal to 3. If x is 2 plus y is equal to 3, we'll subtract 2 from both sides and get y is equal to 1. That tells us that our final answer is the point when x is 2, y is 1. Alright, let's take a look at some odd outcomes. We've seen infinite solutions. We've seen finding one exact solution. Alright, what else could there possibly be? Let's look at this system of equations. X minus 3y is equal to 5, and negative 2x plus 6y is equal to 8. We are going to continue here by solving systems by elimination. Alright, and sometimes they require a little bit more manipulation before we see what can cancel each other out. Alright, so I just like to rewrite it to get us started. Here we have x minus 3y is equal to 5, and negative 2x plus 6y is equal to 8. Now we want to either add or subtract these two equations in order for either the x or the y to be canceled out. Okay, well, let's go ahead and look at x. If we want positive x to cancel with negative 2x, we need a positive 2x here. Well, how are we going to end up with a positive 2x? We can't just make another x appear so that this works out properly. But what we can do is multiply this entire equation by 2. Let's see what happens when we work this out. We'll end up with 2x minus 6y is equal to 10. Alright, we didn't need to change the bottom equation. We're still left with negative 2x plus 6y is equal to 8. And now we have a positive 2x and a negative 2x that will cancel themselves out when we add the equations together. So let's go ahead and add these equations again. Let's put parentheses around this bottom equation. So positive 2x plus a negative 2x, that gives us 0. And then we have negative 6y plus a positive 6y. That also gives us 0. Okay, we have to keep going. We have 10 plus 8. That gives us 18. And so we have that 0 is equal to 18. But we know that can't be correct, right? No way. 0 is certainly not equal to 18. So what does that mean? What is going on here? Let's go back to Desmos and take a look. Alright, our first equation is x minus 3y is equal to 5. And then let's graph negative 2x plus 6y is equal to 8. What do we notice about these two lines? Well, we have parallel lines. The slopes are the same. Parallel lines will never intersect. That means there is no possible solution. These two lines will never touch at any one point. So let's come back to our notes and write that down. So we call this an inconsistent system when this happens. Inconsistent system. Alright, so we went ahead and took a look at Desmos, and we said these are parallel lines. And that means no solution. No solution because no intersection. Alright, so now we've seen infinite solutions on one line. We've seen a singular solution. And now we've seen no solutions. Let's move on to example 4 to see what else is possible. So here we have x plus y is equal to 2, and 2x plus 2y is equal to 4. Again, we're going to attempt this system of equations by elimination. Alright, we'd like somehow for the x's or the y's to cancel out. So if we're looking here, we have positive x and positive 2x. If we want them to cancel out, we need something to change a little bit. So let's go ahead and multiply this top equation by negative 2. That way we'll end up with a negative 2x, and that'll cancel with the positive 2x. Alright, so we have negative 2x minus 2y is equal to negative 4. And we don't change the bottom equation. We have 2x plus 2y is equal to positive 4. We're going to add these two equations together. So here we have negative 2x plus a positive 2x gives us 0. Negative 2y plus a positive 2y, that also gives us 0. And then negative 4 plus a positive 4 also gives us 0. So what we have here is that 0 equals 0, and what does that mean? Well, in our last example, we saw that 0 was equal to 18, and obviously we determined that to be incorrect. Here we have 0 is equal to 0. It's not necessarily a wrong statement. In fact, it is correct, but what does it tell us? Because we weren't able to solve for x or y. All right, well, 0 is equal to 0. We knew that already. We will call this a redundant system. A redundant, or sometimes called dependent system. When we get the fact that 0 is equal to 0 or 2 is equal to 2, any number is equal to itself, we call it a redundant or dependent system. Well, what does that mean in terms of solutions? Let's go back to Desmos one more time today and see what we're looking at. Alright, so here we have x plus y is equal to 2. And let's now graph 2x plus 2y is equal to 4. Now, did we catch the color change? X plus y is equal to 2 was the red line, and then when I asked it to graph 2x plus 2y equals 4, our red line changed to green. What this is showing us is that our two lines are in fact the same line. If we're looking for where our two lines intersect, well, they are the same line. They intersect absolutely everywhere. We are back to infinitely many solutions. Let's go back to our notes and write that down. These are the same line. One just maybe was a bit more disguised than the other, but truly they are the same line. This means we have infinitely many solutions. And again, we could parameterize them and find the general solution if we were asked to do that, or we can just note that it has infinitely many solutions. So to recap, what are the possible outcomes for a system of two linear equations? Well, we've determined that we could have infinitely many solutions. We could have no solution. That's a possibility. If our lines are parallel, though they will never intersect. Or we could have one solution. If a line intersects with another line, they will only ever do so at one point unless it is the same line. In that case, they will intersect at every point. Alright, so now let's take a look at how we can use this knowledge on solving systems of equations and apply it to some larger word or application problems. So let's go ahead and read through example 5. We have a company, Acme Baby Foods, and they mix 2 strengths of apple juice. 1 quart of beginner's juice is made from 30 fluid ounces of water and 2 fluid ounces of apple juice concentrate. I'm going to go ahead and highlight that. That seems important. Alright, so beginner's juice, we have 30 fluid ounces of water and 2 fluid ounces of apple juice concentrate. And then 1 quart of advanced juice is made from 20 fluid ounces of water and 12 fluid ounces of concentrate. This also seems important, but I'm going to change my highlighter color since now we're talking about advanced juice. Alright, so advanced juice has 20 fluid ounces of water and 12 fluid ounces of concentrate. Each day, Acme has available 30,000 fluid ounces of water and 3,600 fluid ounces of concentrate. Again, seems important, changing my highlighter color because now we're just talking about the company as a whole. Alright, so 30,000 fluid ounces of water and 3,600 fluid ounces of concentrate available in a day. If the company wants to use all of the water and all of the concentrate, how many quarts of each type of juice should it mix? Alright, so we have a few steps to breaking down a larger application problem like this. The first thing that we should do, so step 1, we should identify and explicitly label what we need to find. Alright, too many times we start trying to add or subtract things together, we get to what we think might be the end, and then we weren't quite sure what we were supposed to be finding in the first place. So it is very important to start by identifying and explicitly labeling what we are trying to find. So let's reread the question. If the company wants to use all of the water and all of the concentrate, how many quarts of each type of juice should it mix? That's the question. How many quarts of each type of juice should it mix? Alright, so let's go ahead and identify our variables. So we're going to say that variable x is the number of quarts of beginner's juice. Right? That's the first type of juice that was mentioned in the problem. So I'll go ahead and give that the variable x. And how about the variable y? Well, that's the number of quarts of advanced juice. Now, if you would like to use the variables b for beginner juice and a for advanced juice, or any other combination of variables, you are more than welcome to. X and y are typically the variables that you'll see in a math problem in two variables. That's why we choose to use them here. Right, but as long as you identify them properly and clearly and use those two variables throughout the problem, you can choose any two variables that you would like. But with that, we're done with step 1. We identified and labeled what we are trying to find. Alright, so now we need to set up some equations. How are we going to find these variables that we decided we need to find? Alright, so that's step 2. Step 2 is to set up our equations. Now sometimes we can use a table, and whenever we can use a table, that's always going to be the most helpful way to keep all of our information organized. Alright, so let's go ahead and set up a table, and our table is going to look like this. So we're going to have beginner's juice up top, beginner's juice, and I'm going to just remind us that we are using the variable x for beginner's juice. That'll be the first column. The second column, that's going to be advanced juice. And we're using the variable y for that. Alright. And then the third column, this is going to be the amount available. For example, the amount that Acme has available in a given day. Alright, so we always put what we're trying to find on the top of our table. What we need to find goes on top of our table. Alright, now we need to determine the characteristics, and those are going to be the rows of our table. So let's go back and look at our problem. What did we highlight? We highlighted that beginner's juice is made out of both water and apple juice. Advanced juice is also made out of water and apple juice concentrate. Those are the characteristics of beginner's juice and advanced juice. So our characteristics go down the side of our table. Here we have water as our first characteristic and concentrate as our second characteristic. Alright, let's make a note of that. Characteristics go on the side. What we need to find goes on top. This is very important because this is how we're going to set up our equations. So, beginner's juice, let's zoom out so we can see everything here. Beginner's juice uses 30 fluid ounces of water. It also uses 2 fluid ounces of apple juice concentrate. Advanced juice uses 20 fluid ounces of water and 12 fluid ounces of concentrate. The amount of water that Acme has available in a day is 30,000 fluid ounces, and for concentrate, 3,600 fluid ounces. Alright, now in order to set up the equations, what we've done now is set up a table to help us set up the equations. But to finish the equations, we're going to read from left to right across each row of our table. So here we have 30 ounces of water per quart of beginner's juice. So that means 30 fluid ounces for every quart of beginner's juice, and the number of quarts of beginner's juice is represented by the variable x. So 30x. We also have 20 fluid ounces of advanced juice per quart of advanced juice, so that would be 20y. Well, if Acme wants to use up all 30,000 fluid ounces of water it has available, then 30 fluid ounces times the number of quarts of beginner's juice plus 20 fluid ounces times the number of quarts of advanced juice, well, it must add up to, it must equal that 30,000 fluid ounces. If we read across the bottom table, or the bottom row of our table here, we have 2 fluid ounces per quart of beginner's juice plus 12 fluid ounces per quart of advanced juice. That must total 3,600 fluid ounces. Alright, so now we are done setting up the equations. We're done with step 2. Our third step now would be solving our system of equations. Let's see, I'm going to go ahead and move this comment over to the side here. Give us a little bit more room so we can write down step 3. We need to solve the system. Alright, so our system of equations, that's our 30x plus 20y is equal to 30,000, and 2x plus 12y is equal to 3,600. So far, we've been solving systems of equations by elimination, so let's continue that by multiplying equation 2 here by negative 15. Alright, so we don't change the top row. That stays as 30x plus 20y is equal to 30,000. Our bottom row here becomes negative 30x minus 180y is equal to negative 54,000. Our 30x values will now cancel each other out, so that gives us 0. 20y plus negative 180y gives us negative 160y is equal to, well, 30,000 minus 54,000, we get negative 24,000. Finish by dividing by negative 160. This gives us y is equal to 150. Now, have we officially finished solving our system of equations? No, we haven't, because we're looking for a point, and a point contains an x and a y value. So we've found the y value, but we haven't found the x value yet. Alright, so now let's solve for x. Now find x, and just as we did in a couple of examples earlier, all we need to do is plug in our current y value into either of the original equations and solve for x. Alright, so let's go ahead and take the smaller equation, the 2x plus 12y is equal to 3,600. You can take the larger equation if you'd like. This way our numbers just stay a bit smaller, but you'll get the same answer if you correctly work it out either way. So in order to find x, we have 2x plus 12 times 150 is equal to 3,600. This gives us 2x plus 1,800 is equal to 3,600. And if we go ahead and subtract that 1,800 from both sides and then divide by 2, we should end up with x is equal to 900. Alright, so we found our value of x, we found our value of y, our very last step, and we ran out of room down here, so we'll write it over on the side. Our very last step, step 4, write down your final answer. Alright, so our point, our solution point, when x is 900, y is 150, but what does that mean? What were we trying to find again? Let's refer back to problem 1, or step 1, where we identified and labeled what we were trying to find. X meant the number of quarts of beginner's juice, and y meant the number of quarts of advanced juice. So let's go ahead and write that with our final answer. The company wanted to know how many quarts of each should they mix. So we can tell the company that the company should mix 900 quarts of beginner's juice and 150 quarts of advanced juice to use all of their available product. And you could be even more specific by saying to use all 30,000 fluid ounces of water and all 3,600 fluid ounces of apple juice concentrate, but we will leave it as is for this example. Alright, let's take a look at example 6. A medieval alchemist's love potion calls for a number of eyes of newt and toes of frog, the total being 20, but with twice as many newt eyes as frog toes, how many of each are required? Okay, now sometimes some of our problems will lend themselves nicely to being set up using a table. And we saw how nice the table was to read right across a row and we get an equation. And other times we have problems like this that maybe sound a bit more like a riddle or don't necessarily lend themselves to a table. Alright, so we still need to follow our steps. We need to start by identifying what we're trying to find, but our setting up of equations is going to be a little bit different of a process than it was in our last example. Alright, so again, let's start with our first step, and that's identifying what we're trying to find. How many of each are required? Well, what did the problem discuss? It talked about eyes of newt and toes of frog. Alright, so again, we're dealing with two unknowns or two variables in this problem. So x will be the number of newt eyes. Okay, and then y is the number of frog toes. So we've identified and explicitly labeled what we are trying to find. Now, step 2, setting up our equations, might look a little different this time. So step 2, we need to set up our equations. Let's read through this again. A medieval alchemist's love potion calls for a number of newt eyes and a number of frog toes, the total being 20. How could we take this statement, the total being 20, and turn it into a mathematical statement or an equation? The total, that means we need to take both the number of newt eyes together with the number of frog toes, or in other words, we need to add them together. So we need to take the number of newt eyes plus the number of frog toes, and the total being 20 means that x plus y should equal 20. Okay, that's our first equation. But as we saw in our first example today, a single line has infinite number of solutions. If we'd like to come back to this medieval alchemist and tell them exactly how many of each are required, they might not be too happy with just any possible combination. So let's keep reading and see, is there anything else that we can take out of this question in order to come up with a second equation so that we can give them a more definitive answer? So the second half of that first statement says, but with twice as many newt eyes as frog toes. Twice as many newt eyes as frog toes. Now sometimes we might get a little excited and start writing down our numbers and equations before we've truly thought through this statement. Alright, the best way to think through this statement is to rewrite it. Alright, because at first when we see twice newt eyes, we might start thinking 2x. Alright, but let's see, is that true? Let's double check. So twice as many newt eyes as frog toes. We're going to write it out by using this verbiage here, that we've determined x is the number of newt eyes and y is the number of frog toes. We're going to use those statements. So this tells us that the number of newt eyes is twice the number of frog toes. Pause this, read the statement highlighted in blue, and then read the statement that we just wrote together using the terminology from step 1. Make sure you agree that they mean the same thing, and now let's take our statement that we just wrote and convert that into an equation. The number of newt eyes, that is the variable x, is, in mathematical statements, is represents an equals sign. All right, this is the word twice. I know it doesn't look like there's an extra C in there. We'll add that. There we go. Twice, so 2 times the number of frog toes. Frog toes is represented by the variable y. So let's put it all together. Our second equation is x is equal to 2y. Now we have one more step here. We need to make sure that our equations are written in the proper form. All right, now we might be used to thinking that y equals mx plus b is the proper form. That is our slope-intercept form. But when we're working with systems of equations and we're trying to use elimination in order to solve them, we would like all of our variables to be on one side of the equation. So how we're going to do that is move this 2y over by subtracting 2y from both sides. All right, so therefore we'll get negative 2y and then 0 left on the right-hand side of the equation. Again, pause this video if you have to. Double check you understand what just got moved here. All right, that's our system of equations. Those are the 2 equations we're done with step 2. All right. So finally, step 3, we need to solve our system. I'll write it over here. Solve. Again, we're trying to use elimination. So we have x plus y is equal to 20. X minus 2y is equal to 0. You can do 2 things here. You can either multiply the top or the bottom by a negative 1 to get the x's to cancel out, or we could subtract the bottom equation. That's essentially multiplying by a negative 1 and then adding them together. You could also choose to eliminate the y instead. It is up to you entirely, but I'm going to go ahead and just subtract our bottom equation here. So that means x minus x is 0, y minus a negative 2y, so that ends up canceling out here. Our negative with a negative becomes a positive, right? So that gives us 3y plus 3y, and then 20 minus 0, well, that just leaves us with 20 on the right-hand side. Divide both sides by 3, and y is equal to 20 over 3. And you can simplify this if you'd like to. You can write it as a decimal if you'd like to. Most online systems will want an exact answer for a homework problem, and so they will only take this fraction here. Just a little note about that. All right, but again, we're not yet done. We found y, but we still need to go ahead and find x. All right, so find x. We can take either of the original equations. Here we have x plus y, y is 20 over 3, is equal to 20. And if we go ahead and subtract 20 over 3 from both sides, that gives us x is equal to 40 over 3. And again, you could write these in decimals or make sure you leave it in fraction form for any online homework system that requires an exact answer. But if we want to finish up with step 4, our final answer, when x is 40 over 3, y is 20 over 3. And again, remember that the alchemist, if we're rewriting our problem statement and solution, the alchemist needs to use 40/3 of x was number of newt eyes, and 20/3 of frog toes, that was y. And with that, we are finished with section 3.1, covering systems of 2 equations in 2 unknowns. I hope to see you back here for section 3.2.